So, shall we start? So maybe we should start. Yeah. So welcome to the last session of this workshop, the Open EDA Tools and Design Methodologies. My name is Qiang Xu. I'm from the Chinese University of Hong Kong. So I actually reshuffled the order a little bit about the talks because right now is 2:30 a.m. At Beijing, and the Professor Hailong Yao is right now still with us, right? So we want to get him to talk first, right? So Professor Yao is a full professor at the University of Science and Technology, Beijing, and he's working on EDA for many years, published a lot of paper. So without further ado, I'll just give the floor to Professor Yao. Okay, go ahead.
Thanks very much, Professor Xu, for the introduction. And it's my great pleasure to share our work here. And it's a pity that due to time conflicts, I cannot attend this great meeting to talk with you in person. So now I will share my screen. So sorry, Professor Xu. Can you hear me now? I think there's an issue. I'm using the browser to connect to a meeting, but the browser seems cannot share screen. I need to. Can I talk later? The second one. I need to download
sure,
the app.
Okay.
Share the screen.
Yeah.
So, sorry about that.
In that case, let's start with Dr. Ni, right? Yeah. Okay. All right. So.你的 slide 在哪里？哪个是你的？
大 PS 里面。大 PS 里面。
这个吗
？Yes。
不是这个吗？
是这个。
Yes. But we need to. How do we? So he needs to switch. Yeah, he needs some time to fix that. So we start with Dr. Ni first.
Okay.
But how do we switch? Yeah. Okay. All right. So let's start with Dr. Li Weini, right? He just received his PhD from Pengcheng Lab in Shenzhen, China. Right? So go ahead.
Good afternoon, everyone. I'm Li Weini from Pengcheng Lab and the ICT of China. Professor Xinjuan Li cannot attend the GROW due to the complete schedule. And it's my great honor to introduce the IDEA open source infrastructure of EDA. Yes. First of all, I will introduce some background. This is a typical digital chip design flow, starting from the system specification to the final package tester. And the EDA project involves the internal steps with the red letters, including logic synthesis, physical design, analysis, and the physical verification. Okay. In the recent years, there is a trend that with the increasing number of the open source EDA tools, this reflects a shift of the industry with researchers and developers and organizations which also recognize the benefits of the collaboration and community-driven innovation. Yes. So existing open source EDA tools can already be combined into the digital process flow from RTL to GDS. However, with the diverse usage of diverse background of the researchers, the IDEA project wanted to continue advance the open source EDA tools. There is 2 levels in the open source EDA. The level 1 focuses on the multiple open source EDA tools that is independent with the open source AP and open source PDK. However, to facilitate the development of EDA tools, we also need an infrastructure to help the development of the EDA algorithms. Yes, which can help the contributor from the diverse academia background to contribute the course to the open source EDA, which is called the level 2. Yes. So let's move to the IDEA project. Yes. IDEA projects consists of 1 EDA infrastructure and 14 EDA tools, and we have 5 times tab out based on the EDA tool chains. And here I also want to express our sincerity thanks to all the contributors and the users. The EDA infrastructure is based on the decomposition of the substeps and algorithms of the EDA. Yes. And the EDA infrastructure, the IDEA infrastructure serves as the open source software developer kit and the platform, and it has the file system, database, multiple managers, operators, and interface to enhance the development of the EDA algorithms. And there is the case that the placement tool, IPL, using the IDEA infrastructure to implement its own algorithms and flows. Okay. The first module is the logic synthesis. Logic synthesis, it converts the RTL to the technology-dependent netlist with the PBI optimization. And 3 tools are involved: Logic Factory, IMAP, and IATPG. Logic Factory is a cross-tool logic synthesis platform, and it can combine the advantages from the tools in the same level. And also, it focuses on the logical optimization and the telemetry currently. And it also integrates the physical tools of IDEA to enhance the physical real logic synthesis and the adaptive dataset generation for the AI native testers in logic synthesis. Okay, IMAP is focused on the AI-based logic optimization and technology mapping. It is very extensible and has much docs. Yes. IATPG is focused on the automation test pattern generation. It can implement the basic fault simulation and test pattern generation. The second module is the physical design. Yes, the physical design is its goal is to convert the graph level netlist to the geometric level GDS. it consists of the floor plan, placement, CDS, and routing. And 7 tools are involved. IO refers to network optimization, IFP, IPMP, IPL, SDS, and RTO and IRT. IFT refers to flow plan. Okay. It can support the key tasks such as the layout initialization, out planning, microcell placement, and the power delivery network generation. IPMP refers to the power network plan. It is used to satisfy the IR drop. It is IR drop constraint and improve the routability in the following the routing step. IPR refers to the placement step. It is used to minimize the valence, timing, and congestion of the chip on the macro, yes. RCDS refers to clock tree synthesis. It can optimize the clockness for buffering valence, bound capacitance, transition slow, to generate a clock tree with low latency and constrained scale. RTO refers to time optimization. It is based on the static timing analyzer to optimize the network analysis with the timing. It can fix timing design rule violation, fix hold time, optimize the setup time, and also it can optimize the network with the get size, buffer location, buffer insertion, and so on. IRT refers to the routing. It consists of the global router and the detail router. The global router incorporates with the fast standard tree generation algorithm and various routing algorithms. And the detail router iteratively eliminates the design rule violation by a 3D S-star algorithm. Here we also have a comparison with the idea between the idea and the inverse on 30 cases. We can see that after the routing stage, the average suggested frequency of idea is 0.95 over inverse. The last module is about the analysis and verification. Yes, IDEA provides many evaluators to help the development of the new algorithms. And the common metric of the evaluator is based on the time, power, valence, congestion, slow, bound, and so on. And the filters are involved. The first is the ISTA, refers to static timing analysis. Yes, it is used to compute the timing of the path within analysis. Yes, it can support the incremental timing propagation, detailed reports, and precise delay calculation. And IPA refers to power analysis. It excels in the toggle and static signal propagation, to evaluate the power of the analysis. IIR refers to IR drop calculation. It is used to analyze the IR drop of the chip to balance the power, yes. And IDRC refers to design rule check, and it can support the geometry rule check for It can reduce the geometry check with the 28 nanometers and above percent node in the mainstream foundry. And here is an example of the design by EDA toolchain. This is the CPU chip from Yixing RISC-V with at 28 nanometers process node, and the reports and the result is shown in the figure and the right figures and the left tables of further each internal tools. Okay, in last I will conclude the features of our EDA tool. Yes. For the IC designer, it can establish the background physical design flow, and also it supports TIGO language. It can also provide the rich performance evaluations. It supports layout visualization, supports data snapshots and toolchain data recovery. It also has user-friendly and user guides and computing support. And as for the EDA coder, it provides netlist 2 GDS2 interface, and it offers multi-language version interfaces such as C++, Python, TIGO, and Rust. And also, we also have a lot of development manuals and the community support. And for example, this is the info software framework of the API. And this is a multiple programming language interface. Yes. It can also have the multiple data analysis and debug methods to help the type out of the development of the EDA tool. We also can have the data snaps and recovery by the serialization and the deserialization. Okay. This is the documentation example and the manual. Okay. And also we also have rich intermediate data for the development of the AR-EDA. Okay, here is the final conclusion, and you guys can find our open source links at the Git or GitHub. Okay, that's all. Thank you.
So we have time for like a few questions. Any questions?
In what stage of support is System Verilog?
Sorry?
What is the state of support for System Verilog hardware description language?
We now focus on the IEEE, focus on the Verilog IEEE 2005. So it mainly focus on, yes, we focus on the Verilog now.
Okay, thanks.
Any other questions?
Okay. So also complementing the question, I think you based this on the top of IOSIS, is it correct? And also I would like to understand what was the development path for EDA, if it was from scratch or if you used a lot other open source projects.
Okay, sorry. That is.
So there are two questions. So if you base your synthesis over IOSIS,
Sorry?
what's your synthesis tool?
What you synthesize? We use uses.
Yes, yes.
uses? Yeah.
Yes, because the logic senses, we have the logic factory to combine the multiple logic senses tool to support the logic senses step. Because we think it can combine the advantages of the multiple independent logic sense tool. UCC is the one of the logic sense tool, but also there is other logic sense such as IMAP and the tools from the EPI level.
So let's be very, very specific. So do your team develop an EDA from scratch? So this layout tool, all this stuff is from scratch, or did you base it in like other tools, like the other projects?
The physical design is developed by from scratch, yes, by ourselves. But the logic senses, because it has a lot of work to do, so we utilize the UCS and IBC to, yes. Okay.
All right. Okay. Okay. All right. Solve this all. Okay. All right. Let's thank our speaker again, and then we move to the next stop. Okay. Hello. Can you share the screen now? Hello? I cannot hear you. Yeah, I can see the screen, but I cannot hear you.
Can you hear
Okay.
me now?
Yeah. You may need to raise your voice a little bit. All right. Okay. Good. Yeah.
Okay.
We are all set. Oh, go ahead.
Okay. My topic today is intelligent placement and routing methods for 2D and 3D ICs. Okay, this outline. First of all, I want to briefly introduce the digital EDA design flow. So when we get the system specification, we can have the architectural design, and then functional design, and then circuit design. And then after that, we have the net list, and we can do a physical design. In physical design, we have the different steps. I think in physical design, two key stages are placement and route. So my talk today focuses on placement and route. Then after physical design, we can do physical verification and sign off, and then fabrication and packaging like that. So actually, we are facing with the physical limit of the chips. So another way to develop the chips is the integrated chips, or we can name it chiplets. So there are two directions. Physical one is the physical limits. We want to push forward these physical limits. That is called more. Another one is more than more. That is to extend to chiplets. And in the third direction. So this slide shows the development of the different chiplets and the heterogeneous integration. Because my topic focuses on both 2D and 3D ICs, I will introduce something about the 3D IC. We also call it in mainland China, we call it integrated chips. It is forecasted that integrated chips can achieve more than 100 faster computing speeds and 20 times faster greater memory capacity. So there are different types of packaging techniques, including 2D package, 2.5D package, and the 3D package. And there are different features of these packaging technologies. First one is 2D package. So we have this, the feature basically is wire bonding and flip chip bonding techniques. Here are some examples of conventional methods of wire bonding and also advanced method of flip chip bonding. So for 2.5D packaging techniques, we have the interposers, including redistribution layer interposer and the silicon interposer. There are representative technologies like Intel, EMIB, TSMC, CoWoS, like that. Then for 2.5D package, we have the RDL interposer and also the silicon interposer. So for this interconnection, we have the interposer like using the macro bonds, C4 bonds, and the TSVs. Then for 3D package, we have the TSVs. So using TSV, we can we also employ hybrid bonding techniques like wafer on wafer and chip on wafer. And there are representative techniques like TSMC, SOIC, and Intel and Samsung techniques. Another direction of this large integration techniques include this wafer scale integration. And that is to manufacture a single large integrated circuit on an entire wafer rather than dicing the wafer into multiple small chips. So there's another direction. I think all these directions pose challenges to placement and routing. So there are some challenges for placement routing with different types of process nodes. One is the multi-reticle design and alignment issue. Another one is the thermal dissipation challenges. And also there are signal transmission latency and bandwidth limitation challenges. So in the design stages, we need to consider these challenges. So specifically in placement routing, we have different challenges. First one is traditional placement, 2D placement. There are large-scale design challenges, and also the placement quality affects subsequent design stages. So we need to consider the different objectives like variance, density, routability, timing, etc. simultaneously. Then for placement in 2.5D, we need to consider performance issues such as the interposer, and we need to consider floor planning to optimize the interconnection. And there are also reliability issues. We need to consider the coefficient of thermal expansion. And also we need to consider stress and warpage. Then in 3D packaging, we need to further consider the large solution space and also thermal management, because in the 3D integration, heat dissipation is limited. And also there are reliability issues such as electromigration and thermal issues. So thermal wire placement is a critical aspect or area. Then for routing, traditionally for 2D routing, we have these large problem size, algorithm complexity, and complex design rules, also complex circuit constraints for different types of routing scenarios, like analog circuits, FPD circuits, and digital circuits. So these are traditional routing challenges. And then for 2.5D and 3D, we need to further consider the fan-out routing, interchiplet routing, RDL routing, TSV planning and routing, like that. So there are many different problems and challenges. Another a great challenge is I think this is a traditional challenge. This is 2D design. That is the gap, the design gap between placement and routing. This means a good placement result may not correlate to a good routing solution. So that is because during placement, we cannot very accurately predict the routing solution or routing quality. So there is a gap between placement and routing. So this is, we call it co-design challenge. Then for 2.5D and 3D, we need to further consider TSVs and also the complex effects like thermal distribution and stress distribution, signal integrity, like that. So there are many different challenges. Then for the third part, I will briefly introduce existing methods. So for 2D floor planning and placement methods, traditionally we formulate floor planning problem as a combinational optimization problem and solve it using simulated annealing, LP, like that. There are some typical methods. And then for placement, nowadays a good method for placement is analytical placement. We formulate placement as a mathematical optimization problem, and we use differentiable wire length and density models. Then we can do this mathematical optimization. There are some typical placers. So here are some analytical methods in the latest years. And there are also machine learning techniques that are used to do graph planning or floor planning. So this method uses graph neural networks to do floor planning. And also there are some works that integrate the thermal models. We know that thermal is always an issue in 2D and 3D. So integrate thermal model into floor planning can alleviate or reduce the thermal issues. There are also some placement methods using GPU acceleration. So this is based on the analytical placement method. We use GPU and they use GPU acceleration to speed up the placement solving process. And there are some latest works that improves analytical placement methods. There are more works actually using machine learning to do placement in 2D. And also there are some works considering other metrics. For example, this work refines macro placement incrementally using KD tree and also gradient-based shifting to improve timing power metrics. There are also some works that consider RTL information that can further optimize macro placement. We also did some work in this analytical placement area. This work is basically we use we observe that the variance model in placement is not very accurate. Typically, if you want to do analytical placement, we have to design a differentiable variance model. So these are classical variance models, but they are manually designed and suboptimal. So we think that maybe we can try to learn a variance model from the data. So we use some Bayesian optimization methods to learn a variance model, then integrate it into analytical placement. So our method seems working. We can improve HPWL variance by more than around 2%. Actually, this is not very large, but if we improve the variance, then routability will be greatly improved. So I think this is interesting work. We also consider that because half parameter variance is not very accurate, so we consider that we can use rectilinear standard tree models. So we designed a differentiable rectilinear standard tree model, and then we use this standard tree model to directly do placement. So we can further improve the RSMT, or rectilinear standard minimal tree variance, more than 3%. So this is another work we tried in late years. So these are the placement methods. Then here are some floor planning methods for 2.5D. So due to time limit, I won't do a detailed introduction. Some of the works consider warpage and stress. There are also some analytical placement methods for 3D. So one way is to transform 3D placement into 2D and then map back to the 3D. There are also some pure 3D methods. So here's a table. Actually, there's this from our observation may not be very accurate. So we think the placement methods includes simulating the annealing methods, link count placement, quadratic placement, nonlinear placement, machine learning-based placement, and also for large designs, we need to do divide and conquer. So they always have some strengths and weaknesses, and have different application scenarios. So for global routing methods, so we have the some heuristic methods. Also, during global routing, we need to do standard tree construction and routing. So there are different methods. Also, there are some analytical methods and the parallel global routing methods and machine learning-based global routing methods. So the machine learning-based methods use the machine learning models to predict some design violations after global routing. In this area, we also did some exploration. This is one work we did. So this is for standard tree construction. We know that a standard tree, when we do standard tree construction, there are at least two objectives. One is total variance. Another one is the delay, signal delay. So we are thinking that traditionally researchers do balancing the variance and the delay by weighted parameters. But we think maybe there's a way to do parental optimization. So we can find the parental curve so that we can get all the optimal solutions considering variance and timing. So our methods are based on the lookup table and also a local search heuristic to get parental optimal topologies. So from the experiments, our works, I think the performance is kind of good. This is also published in this year's deck. And then for detailed routing methods, there are search-based routing methods, integral linear programming-based methods, and also during routing, we need to consider multiple patterning. So we also did some work in multiple patterning aware routing. So we consider the TPL in the routing. Basically, we did some kind of interesting encoding. We encode the routing solution so that it's very fast, and the routing the solution is interesting. It's also published into this year's deck. And also we tried some escape routing, order escape routing. So this I think this is we use machine learning, Monte Carlo tree search, and the reinforcement learning to find the escape routing solution. I think this is also interesting work. Okay, then for 2.5D, there are different routing methods, global routing method and detailed routing methods. Due to time limit, I won't introduce in detail. Then we also consider the chiplets interconnection work. We have one work considering the where, because where blocks the routing. So this our latest work consider chiplet interconnection routing. For 3D routing, we need to consider thermal. This actually there are very few work in this area. Okay, then this is a table listing the different methods of routing and strengths and weakness. Due to time limit, I won't introduce in detail. Okay. So there are also some commercial tools for 3D design, including placement routing, including Synopsys, 3D IC, and also Cadence and Siemens platforms. And then I also mentioned that there is a gap between placement routing. So there's also a tool in Synopsys, this Fusion compiler. So they try to bridge the gap, I think, is to achieve better solution. So this Fusion compiler. And also Synopsys also gave a tool for machine learning-based macro placement. I think this is also an interesting tool. They use machine learning to predict the macro placement quality. So then they can choose a good macro placement solution. Then anyway, there are some there are details. Okay, then future direction. I think for floor planning and placement, there's different design technologies. And also, we need to do parallelization and 2D, 2.5D and 3D integration. We need to consider thermal stress, electromigration, and also the related prediction. For routing, the challenges or directions are similar. So we need to consider the 3D integration, multi-physics convergence, and the cloud-native architectures for speed up. Okay, then this we come to the conclusion. I just briefly introduced the placement routing for 2D, 2.5D, and 3D. We also introduced several our latest work. I think there are still a lot of work to do considering 3D IC, because there are thermal, mechanical, electromagnetic, and optical signal integrity issues. So there's left for our future work. Okay, then this concludes our my talk. Thanks very much.
So we have time for one quick question.
Hello, thank you for your presentation.
Thank you.
I would like to know if you have all this information. It was really dense. If you have it already published somewhere that we can read it, and if you have left a copy of your presentation with us to consult later, because congratulations, it was really dense, really interesting.
Yeah, sure, no problem. I think our work are only a few works. There are many different works. These are citations, different works. We just do an integration, investigation of different works.
So hello, can you basically like share your slides afterwards?
Sure.
Okay.
Yes.
All right. So I'll share the slide.
Yeah,
All right.
yeah.
Okay. So
Okay,
that's
thank
it
you.
then. Hello. Well, you need to go to sleep, right? So it's like
Thank you.
3:30, right? Okay. All right. See
Thank you
around.
very much.
Okay.
Yeah,
Bye-bye.
see you. Thank you.
Okay.
Bye bye.
So we need to switch to yeah. All right, so our next speaker is Professor Rodolfo Azevedo, right? So he's a full professor at the University of Campinas. So
Thank you for the introduction. Hello, everyone. I will start to talk about the Process OCI, which is a project that we are holding at the Unicamp. It's focused on continuous integration and RISC-V processor design. Indeed, I'm here, but those guys on the picture are the ones that did the work. And plus this one who didn't send me the picture. And just to be recorded and complain to them. Just to show some previous experience, back in 2015, we published a paper on ISCA telling about reduction instruction set. How can you reduce the instruction set of a processor? And we managed to reduce the x86 by 40% of the instructions. And then if you did that, we could improve the code performance and also do not penalize the program executions. So 2 of those students later on went to Meta and they work on compilers over there. Later on, we tried to verify processor on cross-platform, and we verify like power processors against ARM processors, so by multiple architecture. And one of the interesting side effects is that we try to validate the processor, and then we found bugs in GCC, GDB, because they use unspecified they use instructions configured to unspecified behaviors. So it's not correct to use. And later, as a side project, we asked one student to pick the Spark Leon 3 processor and redesign the decoder to make it a RISC-V. It is still available over there. And later on, Lucas went to NVIDIA to work there. So this is some of the brief work, but to start my presentation, I will need to read a very small text for you just to make it a little bit creepier for you. Between Christmas and New Year's Eve 2017, something strange began to unfold. Unusual patches were silently landing in the major operating systems. Kernel changes with vague names, no public explanation, no deep implications. Rumors spread. Was there a major CPU flaw? Were the vendors hiding? Then, on January 2nd, a leak. By January 3rd, the truth was out, Spectre and Meltdown appears. 2 vulnerabilities that shatter long-held assumptions about processor security. What was supposed to remain secret until June 9 exploded into public days earlier. Months of quiet panic turned to global scramble, right as the world was returning from a holiday. So this is just to motivate you. How many district providers of RISC-V cores will your cell phone or your car or your device have? Are all of them safe for you? Who will test them? How they are going to check them? And what can you do by that? This is the goal of our processor. When you need a new RISC-V core, usually you can try to start from the core from scratch. You can get architecture specification, performance requires, and you start from everything. You can buy a core, as you can do with any core. You have price licenses and performance. You can use an open source model, so you need to select which one. We are going to focus on the third option. You can do the other one, but most of the problems will be faced by all of these options. And if you try to go there, about 1/3 of the RISC-V processors on RISC-V.org did not even compile. So just download them, try to compile. They're not going even to compile. You cannot check in this way. And then we start with this challenge and work out. And currently, one of our students were working here side. Every time you mention a new process, he get the link, the GitHub, and try to add to our infrastructure. Currently, we have Process OCI has already 103 cores, distinct cores, and we are trying to work on that to improve and try to verify in large scale distinct RISC-V cores. We do that using FPGAs and also using simulators. But there is one more thing. You can also do research on that too. And our goal in this direction is try not only to verify the project, but to find out new methodologies that you can work to verify the project. And the key idea is that if you look like papers published on RISC-V verification along the year, this red line is keeping increasing, and this motivation, the research that was almost stable on processor verification, and then it keep going. So people are moving to verify RISC-V processors because it's open source, and then we can share the results from one category to the other. And but mostly, the paper verifies 3 processors, 5, 1, and suddenly you found out this one with 12 processor, and okay, let's read it, let's find out it was 12 configurations of the same processor. So it's not exactly 12 different processors, but the same one with several configurations. So the 103 we showed to you are 103 different distinct GitHub links from them. The key idea, and I'm returning from this picture, Sandro presented this picture last Monday. And he talked about the right side of this picture, and I'm going to talk to you from the left side of this picture. We need to check both valid and invalid instruction. And one key component is that what if your processor has an extra extension that they didn't mention to you? And then you can ship a code using that extension and do anything you want. It's not difficult to do if you know how to design a processor, but you can try to do. So you need to check a valid instruction must be valid, and invalid must be invalid also in this direction. So what do we do? Currently, processor verification is not exactly standardized. You can do things and you can run software. You can inspect the processor. You can do different things. Multiple users, ISAs make reusing very difficult. If you have specific code, specific implementation, you cannot reuse that. Proprietary implementations make sharing verification framework thoughts. It's not that easy because you have several different tools, and you need to verify different synthesis, verification flows, complicating reusing. And even for open source, and you find out several open source methodologies, and the first thing they do, and it's not exactly a flaw, but you say, oh, my process is really easy to use. Just get the container and run that. But now I have your container, the other container, the other container, the tools and everything else. So I have difficulty to share exactly the same infrastructure for all of them. And when we talk about the RISC-V committee, they are trying to move in this direction. They have the compliance committee. They have like RISC-Off, they have SAIL, Spark, and they have some process-specific approaches, which is very good. But they are not tied to verify multiple processors with the same common methodology. You need to re-implement everything. And that's what we are trying to face and move. So 103 distinct processor implementations. And if you go to the website, it's already available. You are going to see 4 distinct labels for each for a processor. The first one, build, not run. So it's not exactly integrated yet. It's under integration at this moment. This processor is going to be integrated. We have the repository. We have downloaded it, but we are under integration. We have the failing one. So that 30% of the processor that I mentioned to you that did not even compile, or you have a very basic error. We have the unstable one. Everything is going pretty well, but there are some bugs that we found out on the processor, but it's going directly. And we have also the passing one, the green one. And we are creating these labels so that we can share back with the processor, and they can put this status on their GitHub, because we can share back the status of them. What do we have under the rule? We have two sets of configurations, the hardware one on FPGA, and we have also the software one over there. Let's start with the hardware one. We have here an FPGA. And this FPGA, we have our controller here and the processor itself. So we can reset the processor, do the basic thing, but we can also remove the clock. We can completely inspect the memory of the processor. We can stop the processor, get all data from the memory, change the memory, and we can change the software that's running. So we do everything from this part. And indeed, this part is controlled by a software that's running on our PC, so on our server. So we can remotely control everything that is running on the FPGA. We use Jenkins as a continuous integration tool. Although GitHub has continuous integration, I must be the owner of the repository to apply. So we use Jenkins with the link of Git, and then we pull the repository and get all the data. So Jenkins also orchestrating the entire testing processes, produce a complete pipeline for building and running, and you can then apply the same tests for every processor whenever you have a compatible setup. And we also have the entire execution history, so you can go back. If you find a bug today and it's not yesterday, you can find it, and you can see the command line that generates the bug. We are testing. We have already 7 FPGA boards supported. We are focusing mostly on one, but we have all the others supported. We simulate with CocoTB with multiple simulations and languages. And we also are evaluating using large language models to help us detect information from the processors. Just to go one picture for you. This is one processor. We have the pipeline, clone the Git, try simulating the processor, try to use some utilities, check on 2 different FPGA boards, and if everything gets green, your processor is ready. And this one is clicked here, so you have the log of all the comments here, and you can get the comments from the CI here. We also are using AI to help connecting the processor to our infrastructure. Indeed, if you think about some of the processors are provided with the SoC, and we need to cut it out of the internal SoC and get the specific core to our device. And we evaluated 21 open source AI models to select the correct source files, the minimum necessary source files, select the top model, create an instance, extract bus type, because they have multiple bus types, including custom bus types, and try to connect to us. And we have a paper on this that we are writing right now. So we have the distinct ones. Some of them got more than 7% of the results correct, but not all yet. We are working on this direction also. And after you do that, we can also collect performance area and statistics for all processors. So these are some of the supported processors. Consider one FPGA, and you have area and frequency, and you can plot them and help you to select the ones, and try to compare them also against each other. And additional tools that are working at this moment, we have the processor inspector. It's an AI augmented process characteristic collector. So what do you know about this processor? How many information can we get from this processor? We try to use AI to collect this. And also some of the processors, they have like configuration flags at the beginning. We need to extract, and we try to collect this. We have the software inspector. If you give an ELF, a binary or a memory blob, it detects exactly RISC-V ISA extension required to run that. And you can do also the opposite. You can generate random software for you. So we are working on this direction. And if you work with these two together, you can select and know if the processor supports or not some of the extensions. We are working on the processor inspector, the performance inspector to collect performance and all the information from them. Security inspection, this is a new step. We are going to look for rogue instruction extensions, and also the processor selector that has all the other features. So, okay, which process do you want? How is the level of maturity that we have on this processor? And that's all I have to. Thank you very much.
All right. Any questions? I have one. Yeah. Yeah. What does it mean fast now?
At exactly this moment, we have a set of programs. So it compiles, it runs on FPGA, and it runs a set of programs that we have available at this moment. Yes, definitely. Yes, path is going to be. You are right. At this moment, since you have the black one that is not exactly running, we are keeping the path with this kind of undefined behavior. Whenever we move this one to the middle, we are going to have the path in the future. We are going to have like path by extensions and path by different kind of tests. Okay.
Are you using mostly the distributions available in the GitHub that usually are monocore or 2 or 4 cores? And I do believe that eventually the problems start to exponentially grow up as we increase, and that's a clear trend on AI, the number of cores. Do you investigate this direction too or not?
We are planning to investigate like the bigger cores. We have some bigger cores here, but at this moment we are verifying only a single core instance of them. We need to move our infrastructure to multi-core. Then we are going to have buses and all the other stuff. At this moment we are focused inside the core, and then later on we are going to move that. But still we are focused on the smallest one. Personally, I think the smallest one may present some sort of challenge of verification in the sense that we are going to have lots of those devices and people think, oh, it's so simple that I cannot make it fail. But it's very easy to find a core with the simple bugs that keep running. People have devices with them. So we are focused on both the spectrum of the performance.
All right. So let's thank our speaker again. All right. So our next speaker is Dr. Liza Costa. She's from University of São Paulo, right? So, yeah. Finance.
Você não baixou.
Claudia?
So, thank you very much for the invitation to talk. Today, I will talk about So, today I will talk about our chip, the Border Collie, but I've talked about this in the morning. And so I invited Dr. Bruno to help me with a presentation about Open EDA that we are started to using in the program, in the Caninos Locus program. So we have the Internet of Things, billions of devices communicating, and all of them with computers. Not just in the city, but in the forest, in the industry, agriculture. And thinking about this reality, we came out with this program, Caninos Locus. And the idea is to have a Brazilian computer as a module. So we have this platform that could be used inside any product, computing product, and it would help to have a shorter time to the market and have more reliability and leveraging the Brazilian companies to use. So help this ecosystem to have more Brazilian designed products with electronics. And our focus is in this edge computing, that are the devices that are in the final application, the sensors, actuators, smart fridges, everything that are in the end. For example, we have here in University of São Paulo campus, we have some semaphore controllers, right, the lighting for the cars that are powered by Caninos Locus. So we have Labrador and Pulga inside it and doing the control of the timing to open and close using computer vision processing and everything. So our program, it came the full stack, right? When you look for people when people are looking for a job, they say, okay, I'm full stack developer. Here is a little bit different. We mean from the application, software, algorithms, architecture, package, circuits, device, structures, materials. So we want to have this domain, right? This knowledge in Brazil. And this is what we are working for in the past years. In order to do that, we use this methodology that we briefly talked today, that's heterogeneous systems co-design. So our engineers, they have this whole stack vision, and they can navigate and contribute in different levels, think about having accelerations and contributions, since the manufacturing until the designs of the chip or the software. Okay. And one aspect is this that we were discussing now in the past presentations, that is the system in package, where you have several dies, right? Several small chips inside one package. And we can use many different processes and not only integrate it in 2D, but starting to make stacks of memories in order to have the memory really close to each other and to be able to improve the speed and performance of the systems. Okay. Then we decided to do this family. We have the Flea, Labrador, and Bencar, and it has been a really intense designing work. And we have passing through the product design, PCB, SIP, die design, and so we are going through all of this currently, we have this part that's doing on foundries, the fabrication of the chips. And we are working about having this knowledge, so we select open source things, open hardware, and one problem that we have is the EDA, right, to do the design. Because currently we use systems that are closed and proprietary from companies. We have Cadence, and so this is the design flow. I'm thankful for the past presenter that he has shown it in details. And we have several tools that are licensed by these companies, and they are really expensive. For example, we were licensing one of these tools, and it was about 100,000 reais per developer. And it was for the university. So it's really expensive. Bruno has some other negotiations together with SB Micro that for university they can have it for less. But in general, they are really expensive, mainly for companies that will need to use it in order to do products. And when we are discussing analog design, it's really complicated because we have many, how can I say? Yeah, the design, we have many other things to simulate and many aspects as the capacitance of the elements, maybe the wires that go inside the chip that can include capacitance, inductance, resistance, and all of this starts to interfere with the system, and it complicates a lot the system. And when we are talking about 3D, it gains more and more. So our idea was, okay, we have these tools that are fantastic. We are really happy using them, doing our work, and it's all working. But let's start to investigate how can we change these projects to open source EDAs. And then I will invite Bruno, because we are starting this group in University of São Paulo to study and investigate these aspects.
Thank you, Liza. I would like to start my part of the presentation looking at most of our design effort at the later stages of chip development is really linked to development flows. And as I see we have a very heterogeneous group here, I started the presentation trying to just prove, or at least to show to the general public, that we can design chips, or we can go through this flow without paying anything. So we can go to silicon using open tools. And I will really cut this subject, because I think we can do a full week just over these tools, as you could see in the last presentation. I would start just with a brief view of a very interesting flow, which is based on open road. It's complementary to what our friends from China showed before. So if we start with the digital flow, we have here the path to get into the GDS. So we can start with synthesis, as you do with your FPGA. Then you can start with floor plan, placement, clock tree synthesis, routing, and other final tasks. I see we are really simplifying the stuff here. But the important thing is that you get your RTL and you get the GDS at the end. And all of this is already fully built and open source. You can run it with TCL or Python. You can go with this in a matter of maybe one day. So we are using this with the students in parallel with the project. Also, I would like to try to push our public to know a little bit about another flow. We talk a lot about RISC-V, about RTL, but I would like that we understand that we have the analog blocks around. We have high-speed drivers, we have PLLs, and this we also can design with the open source tools. And I will do a very briefly overview of this, mainly trying to show how we can generate these blocks. So we can get schematic entry with Xchain, we can get simulation already for free with the NGSpice, which is really great tool. We can have Xites also, and we can do the layout also. And so just to get an idea what you can get for free, so here we have here Xchain. It really looks like maybe Virtuoso, schematic editor or something like that. So you can use it. Sometimes the students see that this is easier than the Virtuoso option. Also, we have several layout tools. Here in the left here we have the Magic tool, which is really old, but it's stable. On the right we have K-layout, and it already implemented several interesting things, like you have here PCL generator stuff. So you can build the tools that automate some design tasks that are really hard for the analog designer. And going back, how we design a chip or at least an analog part, sometimes we start with approach some books or from maybe today GPT stuff, or we get an idea. I like it a lot, the automated design strategies, or trying to use AI or optimization inside the flow. And this is where our first contacts of using open source EDA tools in USP, I think, started. Why? So we had two big works in the past, I think more than 10 years ago right now, which uses a lot of compute power. So we generate one spec on a tryout of a circuit and try to use some algorithm like simulated annealing or genetic algorithms or some kind of artificial intelligence and run it through a lot of tries. And in this time, we already had Cadence, Synopsys, and a lot of tools. So what this thing did, it breaks our license system because we need a lot of compute power and a lot of simulations. And in this time, we understood that NGSpice was a really great tool for that. And we did this work for scheduling in energy, and this, which is the system design, and it's 10 years ago already. So we do a full system design, even analog stuff, with this kind of optimization. So we do block and system level. And also we started to use it because CERN asked us for a big chip. We need to design it. And I was trying to see where was the first time we used a EDA tool which gone to production, like real silicon. Is not a silicon like a sample for 1-2 students. Is like $1 million project with thousands of wafers, which used open source tools. And if you see, I am pushing here from SVN before CERN even does not use Git. So like 10 years ago, we are already using IOSIS inside this project. So I'm proving that open source tools were already inside this project. And this was a real production place. It was not fully designed with open source tools, but it has a big impact on our flow. We had several thousands of runs of this in parallel to check, to link. And what I have to say that this thing worked, and this thing had 5 members in the family. This thing is already installed, and we have thousands and thousands of this fabricated. And I have the full wafer here. And I'll pass you if you want to see. And this was partially or goodly based on some of these tools. So I can say that these tools had an impact on our project. It was not fully done with open source. We used Cadence, we used Synopsys also, but it was important for us. And this was 10 years or 12 years ago in design. If we understand that in the last, so like 2017, we had started to have a lot of growth in the open source community to put effort on these tools. And we started to have better tools, community increased, better tools, more community. Then we had open PDKs. And with this, our group started to understand it's very interesting if the students start to like this. And we started this group, which is Open Silicon, and I will present the last year results of this group for you right now, just to prove that students can design with open source tools also. And we show, in Brazil also, and Brazil and any kind of any place of the world, actually. This is free, and we can even run it in Labrador if you want. These tools are very lightweight. So Brookhaven National Laboratory also wanted a chip. We are designing it. And one of our students had an idea, one new algorithm for a filter. And we made a chip for this application. It was a small chip. And this is fully open source from scratch. And this is a picture. And what I have to say for you is that a second year engineering student made this chip. Second year. So we have 1.5 years and made this. And the most interesting thing that when he was working this, he discovered one new algorithm to do this filtering. It's a kind of medium finder inside the particle physics things, but he discovered a new algorithm. And the thing has good trade-offs. So he discovered doing, when running open road and writing RTL and seeing how if I change it and when I have to do radiation protection, what I need to do, and it discovered an algorithm. Very interesting work. And this was last year. So now we will start, we'll get just one window of 1 year from now. So also we did a VCO, a voltage controller oscillator, to show analog design capabilities. This was submitted in last March. So we have here an analog schematic just to say if, that we can also do the analog design. And here is the layout. You can see we fabricated 6 different chips and just showing one. And this is high frequency IC, so you can see the high frequency probes here and polarization, so it's another difference, not a standard auto-rotated pad ring, so this was custom design. Also, we have serials here, we may also have sound this accelerator, we have a very interesting synchronous light source. We had this idea to build a very fast camera, so a camera that can get mega frames per second, so you can film very small and fast things like molecular interactions or things like that. One student gets design one transimpedance amplifier, which is a block which goes near optics. You can use it with fiber optics, with photonics. And this was also designed through open source tools, and this was sent to IHP in an open PDK in Europe. So it is in fabrication right now. This is the layout. And just to finish it, this is what we are designing this month. So it's a Creo front end for, it's like a VCO and a mixer working in cryogenic temperature for 5 to 7 gigahertz, also using open source tools. So this is going to IHP in next 2 weeks, I hope. And all this effort, it's inside one group I was starting, which is called Open Silicon. It's here, but we intend to generate content that can make chip design accessible for a greater community. And the idea is to use these basic tools, I think we will look to other tools present today to grow the community. It's all summing, so I love the experience here in the conference. And also it's interesting that the students saw this is open tools. I can present this to other people, and they go into one phone we have here and show, maybe we can try to design stuff, and they get money for working with open tool to show the people, just to teach or to make their tape outs, and they got funded. So this is very cool. So the students got alone, no research agency, they got into a fund, and it's a local fund of the university, but it worked. So they got the funding. And just some of subgroups are involved, and also other stuff we are trying to do as an open thing. We are trying to do instruments using open or designs. I would stack just this acquisition system for physics. We have a Linux running there. That's a Debian. So Debian, we are happy. And we also did one ATE. This is a system to test our chips. So we did the chip, and we did the tools to test the chip. This is an expensive machine. It's a multi-million-dollar machine. We tried to do it with FPGA. And just to finish, two of these works have received prizes. This is an open instrument. The guy did one VNA, which is $1 million equipment with open tools running Linux. And that graduation student that made his first tape out got a prize in ISC. It's one of the best conferences in this area. So, which 1.5 year engineering and open tools. So I am very proud of this guy. So I would thank everybody here for the patience to hear me. And I would like to say that maybe we can change a bit our sayings about the scenario. Maybe we can get some students to do many chips, complement your one student on chip stuff. Thank you, people.
That's the first one. So I'll come back to you.
Congratulations, Bruno. Amazing work you guys are doing. I would like to know about the roadmap for the Caninus Locus boards using maybe these open source tools. Do you plan something? Because you have the boards. Are there plans to design chips for these boards using such tools?
Yes, the first step the team was making was trying to get the chips for the Pulga one, the FLIA one, that's the small one. This we more or less are achieving. So we got the RISC-V core, 2 versions of it, it's working, and got the power management. But now one path we can go is to try to do it in open PDK and open tools, because right now they were designed in UMC 65, which is not open PDK right now. So we should investigate to do with one open PDK. So, but right now we got at least the control of the code of these 2 important parts of the small one. And also the guys are working in design a cluster of cores to replace the higher performance one in Labrador, which is one of the main targets of Liza and the team. Thank you.
Okay. Okay. All right. Okay. Let's thank our speaker again. Okay. All right.
I think if you take care, I will pass the wafer. Please don't break it.
Sure.
But so this is a full real wafer from TSMC. So you can see several wafers, and you have the one main ASIC and several test blocks in the side. I think this is the biggest tape out made in Brazil, by my understanding.
Wow. Fascinating.
Yes, this for Sampa going to CERN, it's going to CERN, to China, to United States, Russia, France, and Sweden. So,
So for the ones that do not know it, the wafer is this big thing. It's made of silicon. And inside each square is a different sheet that we call die. The die is each one separated, so we have to cut and put inside the slice with the
Okay.
Yeah, Fafest has sponsored this project.
All right. So our this is going to be the last talk, right? Our last speaker is Aroca from One Brown Labs. Right? So I think you. All right. Okay. Well, okay. All right. I see. I see. Is that this one? Yeah. Okay. Shape Inventor. That's a nice name. It's a nice title. Go ahead. Yeah, go ahead. Okay, so maybe you guys can, take a look at after the the last talk, right? Okay, let's get started.
Okay, good afternoon. My name is Rafael. I'm from Von Braun Labs. And Von Braun Labs is supporting Chip Inventor. We are a startup, okay, that spun off from Von Braun Labs from Campinas. So we thank Von Braun Labs for the support. And I've seen a lot of interesting stuff here. And at DEC last week, we were there. And a lot of stuff happening with open source EDA tools. And I really liked what Bruno said, and we have a lot of synergies regarding the open source tools. And we had some experience with such open source tools for some years. And we noticed that they're not always very well documented. And it takes time to learn everything, to integrate everything, and to get a silicon running. So we had the idea down there at Von Braun Labs of integrating all these open source tools. Right now we have integrated like 40 open source tools into a cloud infrastructure with a web-based access. So this is Chip Inventor. Chip Inventor is a web-based platform that integrates a lot of open source tools and some proprietary tools for the analog and digital flow, both flows, especially for those that are not microelectronics specialists. If you know basics electronics, you can get started and get design with the final GDS files, GRC clean for tape out. So we can get started. This is a quick overview about Chip Inventor. You can do design by dragging and dropping blocks. So we have a lot of blocks, and you can drag and drop these blocks from simple AND gates to complete RISC-V cores. And you can share blocks with other users in a marketplace. So you can share blocks and projects all online, it's on the cloud, and you can work in cooperation with other people. If you are an advanced user, you can use a VS Code-like interface to type Verilog code and work directly in the Verilog, okay? But this approach of the blocks is very good for a high-level overview of the system and to build modular architectures, okay? Well, everything you do, you can synthesize on Chip Inventor Cloud and test on FPGAs. So we have developed a mechanism to load the FPGA bit stream from the design to the FPGA board from the web browser. You don't need to install helper applications like in some solutions. We just use web USB, and from the web browser, you can directly load the FPGA. You can use a smartphone, or you can use a Chromebook, a very lightweight computer. And you can test on some models of FPGAs and prototype quickly. More than that, you can synthesize to several PDKs that are included on the tool. I will show this a little bit more. And we have also integrated some verification tools, waveform visualizers, and some other tools to validate and do simulation. This is a quick overview of Chip Inventor. And a little bit more about this. We start with the chip idea. We have an AI assistant that you can ask for blocks. And from these blocks that are automatically generated, if you want, you can connect these blocks, do FPGA prototyping, GRC, LVS, all the flow that we were discussing during this conference, up to a working device on FPGA or a silicon tape-out. Okay, we have analog and digital support. I'll show a little bit on the cloud from the web browser. And this is curious. We know some commercial tools, and one of the vendors of a commercial tools told us, if you want to work with our tool, reserve 2 months to install, set up, and get everything running. This is not me saying, it's the vendor, okay? So for open source tools, I would say it would take even more, okay? The tools are growing fast, but it takes time. It's a lot of tools to integrate and get started. But we offer first step, very, very affordable and quick, okay? So this is very good for workforce development, startups, professional user, and other approaches, okay? Right now, I heard a lot of people talking about the Sky 130 PDK. We have this PDK. Where is that? We have this PDK integrated with some success cases that were already taped out, okay, in commercial products. The GF180, these first 3 are open PDKs, okay? The IHP 130, Bruno just talked about this PDK. And what is nice is that there is support for the Global Foundries 12, 55, Intel 22, Intel 16, and TSMC 65. We got access to these PDKs. We can now synthesize, but we didn't add to the platform because there is the NDA restriction of these PDKs. But by case, it is possible to use such PDKs. And we have some success stories of very nice designs made for commercial grade products with the 12 nanometers PDK of Global Foundries. And recently, we have an internal need, and we worked on the integration of Silterra PDK 130 and 180. It's internal, but we got some GDS files using this PDK. It's a pretty affordable foundry. Some Brazilian companies already work with this foundry in Malaysia, and we are also cooperating with them. Guys, what I will do now, I will go by some screens of Chip Inventor quickly, just to give an overview of how the tool is. If anyone is interested, we can demo this later, but I will show just some screens to have a gist of how the tool works. This is web-based, okay? You log into chipinventor.com, create an account, you create a new chip. This is analog design. We have a schematics capture. XScan is good, but it's a little bit hard to use, especially Magic. Magic is a little bit hard to use also. You just drag and drop transistors or other components from the foundry PDK. You select the PDK, then you can drag and drop some components. You design your circuit on the web browser, and then you can run SPICE simulation on the analog design that you just did online. You can share with other users, you can share the results, and then you can do the layout on the web browser. I think this is pretty novel. And it's a startup from Brazil. It's our proud, okay? So you have here the layers that you can drag and drop and draw rectangles using such layers. And then you can select all the parameters of a transistor that you are adding to the layout. You can This is the Sky 130, for example, and we are setting the L, the W, the fingers of the transistor, and this goes to the server of Chip Inventor Cloud. It creates the transistor and it brings back the transistor to the web interface. There is magic in the back end, as Bruno can imagine. So you can draw rectangles, metal layers. We even support rerun layer, so you can do a memory, an NVM memory, for example. And we have such case. Then you can run GRC and LVS out from the web browser. So if you want to get started in chip design without the need of installing, configuring all the tools, setting the PDK, etc., you can get started with Chip Inventor. A little bit about the digital approach, okay? Create a new project, we can drag and drop blocks. There are like 300 blocks already available, RISC-V cores, SPI, I2C, CAN bus controller. But you can create your own block by inserting the Verilog and share. And it is a hierarchical tool. So these two blocks here are based on another design. So you design this circuit, and then you can package into a block and use as blocks in another project. Okay? If you want to do something that it's pretty repetitive, you can use an AI and ask for a design that will automatically create a block. For example, some time ago, I needed a MUX with 80 inputs. So I just asked the AI, it created the block, and you can quickly use, it's very useful to help some repetitive tasks, okay? Then we can simulate online, you can verify, you can load this design on an FPGA board from the web browser, as I said. This is the synthesis results for the digital all the way to the GRC clean GDS2 file, ready to send it to the chip foundry. And one of the tools integrated here is OpenRoad. So if you are an advanced user, you can open the logs of OpenRoad. You can see all the details, and you can load specific simulations. For example, you can select an SDF file to do custom simulation of your design. We have a 2D viewer of the resulting layout, a marketplace that you can comment the blocks, share blocks with other users, give stars to some of the designs. And you can do from very simple to very advanced projects with this hierarchical approach. This is a RISC-V core, okay, that is available on the Chip Inventor as a block, and you can load this design, you can synthesize, you can test on the FPGA, and then tape out. We have already taped out in 130 Skywater such design. This is a commercial product that has a RISC-V 130 that was taped out using Chip Inventor. It's how can I say? It's a success case, okay? I wanted to also update, last week we were at DEC, and we have modified the placement algorithm of OpenRoad to run on a quantum computer, a real quantum computer from D-Wave in Canada, to do the placement using a quantum algorithm. Just to let everyone know that we are also working on the basis of the tools, and we plan to collaborate on such results. We are also working with Malaysia and AWS to use Chip Inventor to train a lot of students in Malaysia. They see as a good option to get a lot of students started into the semiconductor design world. Well, we are AWS partners. This is an example of a closed loop control system that was created in 15 minutes. Okay, you drag and drop some blocks, and you can do a closed loop control. This is another example. This chip is out of stock. Okay, you can't buy this chip anymore. It's for robotics. It's pretty expensive. It's hard to find. But you can design a replacement part using Chip Inventor. This is the complete design using some quadrature encoder blocks. You can generate a MUX with the AI, and this generates this chip that can cost cents by doing a full mask, for example. And you can load such design on a low-cost FPGA. I saw the group from the group from Unicamp using this FPGA also. It's pretty affordable to do some tests. Or you can do MPWs or do a full mask, and you get a replacement for an out-of-stock chip. Okay, this is another success case, a Malaysian company that builds drones, and they had a big board with a lot of CAN bus controller, and they needed less weight, less power usage, and less space. So we provided the chip inventor access. They designed themselves this replacement chip. I will be fast here. This is the final layout. And from that 8 centimeters board, they got a 2 millimeter by 2 millimeter design that can be manufactured, for example, in Silterra. Lower power consumption, this was tested, much smaller, from a PCB, complete PCB, to a single chip. Less power. Also, we are talking about a chip competition for the Brazilian students. We call Championship. We are working with the Brazilian government to build this program. And just to finish, this is the RISC-V environment. There is a RISC-V environment inside Chip Inventor that you can program, you can select the RISC-V target, and then you can compile C code and load onto these FPGAs that we provide. So you can quickly test some RISC-V designs. So this is right in time. Okay, thank you guys.
Thank you.
Hello. I would like to know how can we use it, if it's free of charge or if we have to pay a license, if it's open or closed. And yeah, I think that.
Yeah, as it is cloud-based, there is a cost that as a startup, we want to make some money. So everything is open source, and we are asking for a subscription so that you have the synthesis and everything on the cloud. So it starts at $30 per month. Depending on how much synthesis you want to do, it can increase this pricing. But it's mostly because of there is a large workload on the cloud. We are AWS partners, and so we need to pay this bill, okay? However, I'm sorry, we are talking with some sponsors to offer this free of charge to students because of these sponsors, okay?
Hi there. First of all, congratulations on your presentation. It's very nice to see a startup like that one from Brazil. I am interested in the case about drones. So I'm from an organization here called Skyrats. We do drone development in the city laboratory. And if you are able to, I would like to know how was that collaboration like? I've seen the slides, but I would like to know a little bit more, like how was it working with drones? Which features of Chip Inventor do you think they use the most?
One of our goals that I think it was proven with them is we wanted to provide the capability to someone that's not a microelectronics expert to start designing his own chips, and maybe he will go further. So these guys are electrical engineers, but they never worked with semiconductor design. They started using the block design approach, and they designed some CAN bus controller as a block, but they needed 8 of these blocks. Then they copied as blocks, and they were able to test this on the FPGA. I was quick there, but there was some test results here. So this is the circuit being tested on the FPGA. But they didn't need to go into very specifics about semiconductors. They were on the high level of block-based design and some Verilog code. They liked this so much. These are the designs, okay? This is the one of the blocks, another blocks, and all the blocks together. This was so interesting for them that now they want to do other chips. They want to do power control chips, SOCs and other stuff, because they really reduced the space, power, and weight on their product, okay?
All right, so I think we're going to accommodate one last question. So any questions from? Yeah, if not, then let's thank our speaker again.
Well, this concludes our last session of the day and last day of the conference. Congratulations, you survived. I invite Professor Yusuf to join me so we can say a few words. And, well, this is quite a journey, right?
Oh.
And I could spend an hour trying to tell you guys how this came up together, but I'm not sure you will be interested in the details, so I'll make an analogy. Around 8 months ago, yeah, the first, yeah, your first step. But the first meeting that we, I think, met and started talking about this event, we figured out that we have the same interests. We were thinking about doing a small workshop at Unicamp with some people to bring the community together around RISC-V. And then we realized that Zufu had the same interest in doing a community-driven event for RISC-V.
Originally, we heard some rumors about so, and then we said, okay, we should do a workshop, right?
Yeah, and so we started talking about making something bigger, like Rio Grande do Sul and other people that we knew already working about RISC-V in Brazil.
But around 30 people, right?
Yeah, maybe 30.
Yeah.
And then we start talking about that with people from the ministry, people from the RISC-V International, people got interested, and all of a sudden...
And Professor Val said, well, you sent 30 people. I said, oh,
yeah. All of a sudden, the event would be called First Global RISC-V Workshop. Okay? So, if Grow was a startup, we went from being a...
Kira 1 to 9.
Yeah, like
in 60
stealth
days.
mode in a garage in 8 months ago, and global marketing now. So that's the analogy of the ride, okay? And but it was a pleasure to be with you guys this week. I hope you enjoyed the event. I hope you made the connections that we intended to provide.
Oh no, I'm getting old, and I organized thousands of conferences. During this week, I have some fears. I passed some personal problems, so I'm trying to come back to normal activity. I have several fears about losing our colleague Chinese in this massive city, you know. We have 20 million people living here. And then John, Professor Bao, Andrea Gallo didn't show up. So I think I was joking that we are flying, building the plane. I think we should do some acknowledgements. The first is